Hey gang, me again, here to talk to you about buoyancy forces. Many of you are going to have your payload go out into the Venusian atmosphere and you're going to have a balloon above it so that it floats. And for you guys, this is going to be important. Buoyancy force is important for y'all. There's no buoyancy force notes in the InSPIRESS notebook. There's no sheet like there is for some of the other physics equations and stuff. However, there is a PowerPoint on the downloads page on the InSPIRESS website. Go there and download the PowerPoint. It's gonna follow along with what I'm going to talk about today. Hopefully this will be short and sweet and make a lot of sense. But who knows? So anyway, buoyancy force. Buoyancy is basically just it's a balancing act. It's a relationship. So just like the movie Up, actually. So imagine we have a balloon. This is not to scale, by the way. Usually the balloons are much bigger. So, I mean, we have a balloon that's going to be holding up our payload, our mass, right? And so our balloon is going to be filled with a gas. There's a gas outside it. We have a gas, the atmosphere outside, and then we have a gas inside. The buoyancy force buoyancy is pulling us up, and then we have the weight of everything. Weight is pulling us down. So the buoyancy force, in order for our balloon to keep everything afloat, to keep it up floating, and we're going to assume that it just stays afloat, it doesn't go anywhere, then our buoyancy force must equal our weight. So this is what we're going for. Force buoyancy is going to equal the weight. Okay, so on the third slide in the PowerPoint, I've defined what a buoyancy force is. So force buoyancy is equal to the density of the displaced fluid, the rho of the displaced fluid, times the volume of the displacement times gravity. Now, some of you may notice that what a density is just a mass over a volume, right? And so a mass equals to a density times a volume. So basically this is just saying a force is equal to an m times a g, which makes sense, which is what you've learned in physics several times. So whenever you see a density times a volume, just realize that's what we're talking about. It's just a mass. So this is just the mass of things that are displaced times the gravity. So, and we'll get into some more details in a second. So the weight that we have, there's many different types of weight. The weights, there's first of all, there's the equipment the equipment weight. Now, the equipment is going to include your payload down here, the box or whatever your sensors are. There's going to be a cable in there. So here's your weight of your equipment. There's this cable, there's a box down there, something like that. There's also the gas inside here, that you have, it's going to have a weight, the weight of the gas. And then your container, your gas container, basically, it's going to have a weight too, weight of the gas container. So the total weight is the weight of your equipment plus the weight of the gas plus the weight of the gas container. There's three categories. That kind of covers everything. So, and what is a weight? A weight is just a mass times the gravity, right? So the weight total is the weight of the equipment, so it's the mass of the equipment times gravity. And then the weight of the gas, just like up here, it is plus the rho of the gas times the volume of the gas times gravity, plus the weight of the gas container is the rho of the gas container times the volume of the gas container, the density of the gas container, times the volume of the gas container times gravity. So the total weight is just mass times gravity, density times volume, which is mass times gravity, and the density times volume of the gas container, which is mass times gravity. So that's the total weight of the system. So like we said, we're going to set the buoyancy force equal to the weights. And so what we have now, we've got the buoyancy force is the rho of the displaced fluid times the volume of the displacement times gravity equals, we'll make this really big so you can see it, all these, the total weight. And so we're going to have equals, I'm going to write down here for you, the mass of the equipment, sorry, it's a capital E, the mass of the equipment times gravity plus the rho of the gas times the volume of the gas times gravity plus the density of the gas container times the volume of the gas container times gravity. Now here's where we're going to start making some assumptions, okay? Because assumptions are good. Now if we were to be technical with all this, if we were to be really thorough with all this, the displacement, the volume of the displacement includes everything, not just the balloon itself. The displacement also includes the box down below, and there's also the volume of this box displaced some gas. This cable also displaced some gas. So the volume of the displacement is the volume of everything that is, because it deals with the outside atmosphere, the outside fluid. So everything actually displaces that fluid. However, for our purposes, we're going to say that the displaced fluid is equal to the volume of the displaced fluid is equal to the volume of the gas. So this is one of our assumptions. So assumption is the volume of the displacement is equal to the volume of the gas that we put into our balloon, okay? So what does that also mean? That also means that the volume of our gas container is basically nothing, okay? That's what this assumption means, is that the volume of our gas container doesn't exist. So basically the mass of our gas container goes away too. So we've just simplified our equation a lot. Again, this is because of this assumption that the displacement is equal to the gas, which is not exactly true. Depends on the mass. I mean, if your gas container is metal, if it's a metallic balloon, something like that, then yeah, your balloon mass might weigh quite a bit. So what we've essentially done is gotten rid of the mass of the balloon in this case, the balloon material, not the gas inside the balloon or the mass that's hanging underneath it, but the balloon material itself. That might not be the best assumption depending on what you use for balloon material, so please take a look at that assumption. And so what we're left with is we change this to the displaced velocity. So what we're left with is rho displaced fluid times the volume of the displacement times g equals the mass of the equipment times g plus the rho of the gas times the, again, displacement times g. And so you notice that we can cancel out all these g's. It's confusing. Get rid of all the gravities. Because we're in the same location, gravity's pretty much constant. And so we're left with rho displaced fluid times the volume of the displacement equals mass of the equipment plus the rho of the gas times the volume of the displacement. We do a little algebra here, and we end up with the volume of the displacement, which is what we're looking for because it's the volume of our balloon, is going to be equal to the mass of the equipment over rho of the displaced fluid minus rho of the gas. So this is the basic equation that you can use to determine the size of your balloon. That's going to give you the volume of your balloon. Again, based on this assumption here that the displacement is the volume of the gas. Now what this means is that the mass of the gas container is 0. It's neglected. It's assumed to be 0. Okay, that's a big deal. Might not work for everybody, but it helps us define this in an easy fashion. You might want to double check that. If your gas container is heavy, then please look at that. Okay, that's it for now. Thanks a lot. Bye-bye.